In the last video, I have shown you how to set up and use our dynamic reverb system. With update 1.3.1, we have made some small improvements to our reverb graph. The K coefficients have now been set up to scale air absorption based on the distance from the source to the listener. As mentioned before, the higher the frequency, the faster it will decay. We also added a new node called tap delay FF node. This node is a 4-channel delay network with a feedback loop. Internally, it looks something like this. The minimum delay time here is the allowed delay time range of the first channel, and the maximum delay is the allowed delay time range of the last channel. The second and third are anything between them. The feedback gain is the same for all channels. Our actual feedback loop is more complicated than shown here. We don't simply delay and add the output to the input. That will amplify the comb filter effect, which creates metallic artifacts. The outputs are actually mixed together by using a householder matrix. This helps to reduce the artifact. In a high-quality algorithmic reverb, 8 or 16 channels are usually used, which requires high memory and CPU costs. Here, thanks to the modal reverb node, we only need 4 channels. Okay, so our dynamic reverb graph is now complete. We also tested on a wide range of sound effects. For example, DAWs. Compared to the old one. You can clearly feel the weight now thanks to the reverb. Also, vehicle engine effects are dramatically improved. Before, we've always felt like it lacked that spaciness. So the reverb version is now the default bass graph for our card graphs. Now let's discuss occlusion a bit. Sound occlusion might be one of the least developed areas for games. By default, Unreal supports occlusion. You can turn it on here and set these parameters. Like other solutions on the market, occlusion is checked by a simple line trace test between the listener and the sound source. It's fast and cheap, but the accuracy isn't good, because sound occlusion depends on the volume of the obstacle and the distance from the obstacle to the listener. Basically, occlusion filters out mid to high frequency bands of the direct sound, but you can still hear them through reverb. Mid to low frequency bands will either bend around or pass through the obstacle. A simple line trace test will risk making a sound feel over-occluded. Also, you can't really use the same filter parameters for all obstacles. Project Acoustic from Microsoft is the most accurate one for occlusion that I know of, but it requires baking, so it has its limitations. We did experiment with a more accurate occlusion solution by building a 3D Octomap in real time. Octomap is usually used in drone navigation, but it requires quite a lot of memory, and each block update can cost around 100 microseconds. 100 microseconds might not sound like a lot, but it's done per trace, so it adds up over time. After some PAE testing, we conclude that it's better to leave the CPU and memory costs for game logic and scene rendering. Sound occlusion is nice to have, but with all the distance attenuation and reverb, you only really feel its effect on close sound sources occluded by a big object, like a pillar or a wall. So in short, our plugin won't include occlusion, but you can use Unreal's built-in occlusion settings. Just be aware of the cost and the risk. You can reduce the occlusion line trace frequency in your audio component. Okay, so with the new spatialization system, our sound effect pipeline is now complete. For the next major milestone, we want to explore a new kind of synthesizer, to further extend the ability to create different categories of sound with our plugin. It might take a while for the next major update. In the meantime, we will continue to monitor and enhance our system. Bye for now, and I'll see you again once the new synthesizer is ready.